Whole-body tactile sensors are designed to give robots feedback from touch in unstructured environments. The context of which a robot is operating affects the density of tactile sensors needed to complete a task, such as high-resolution pressure data for grasping in cluttered environments, or low-resolution contact detection for human-robot interaction. The primary motivation for our work is that both a robot's shape and operational context influence the design of whole-body tactile sensors, but state-of-the-art sensors only address a robot's shape. In this work, we present GenTact Toolbox, a computational design pipeline that takes into account the shape and context of a robot, procedurally generates whole-body tactile skins that can be adjusted for coverage and density, and instantiates the designs as 3D printed capacitive tactile skins. The pipeline has three main stages: procedural generation, simulation, and fabrication. The first stage defines the skin unit by a set of geometric rules that describe its shape and density. Users start by selecting or painting a skin heat map and a density heat map over the surface of a robot. The skin heat map defines the geometry of the skin unit, and the density heat map defines regions of high and low sensor density. Scalar parameters can then be adjusted to rapidly reconfigure the skin unit. The next stage in the pipeline is to simulate and optimize the density of skin based on the operational context of a robot. This stage assumes the simulated task is an accurate informer of where contact can be expected to occur. As a robot is performing its simulated tasks, each nodule records the number of times they detect contact. Using a modified low-pass Butterworth filter, the contact points can be translated to a new density heat map. The new density heat map is used to redistribute the sensors to be denser in regions of high contact likelihood and not as dense in regions with less likelihood. The last stage of the pipeline is fabrication. In this stage, we 3D print the digital skin units to keep the process ambiguous to shape. This process takes in the final skin unit configuration from the first two stages, connects the sensing nodules together along a single conductive serpentine trace, and prints the wired digital mesh as a multi-material print. The conductive trace can then be connected to a microcontroller for reading and sending data. RC delay capacitive sensing is used in this work as an exploratory case study to demonstrate the real-world instantiation of procedurally generated tactile sensors. As the robot moves back and forth between two end effector states, the skin unit detects contact and the robot moves around the obstruction. The contributions of this work are as follows. 1. A procedural generation algorithm for a new class of tactile sensors. 2. GenTact Toolbox, an open-source design pipeline for whole-body tactile sensors that makes form-fitting skins that adapt to operational context. And 3. An evaluation of our procedurally generated sensors in a physical human-robot interaction use case scenario. Thank you for listening.